Greetings. Today we're going to demonstrate a geographically separated HA cluster by utilizing DRBD, DRBD proxy, Pacemaker, and the newest component, Booth. But before we get into that, I want to discuss real briefly who is Limbit. We're a 15-year-old company. We have operations in both the US and Europe. We are experts in the Linux high availability stack. We are the creators and developers of DRBD. We are the maintainers of the older Heartbeat. We are contributors to Pacemaker. And we are now contributors to the Booth project as well. Real quickly, what is DRBD? It is a block-level storage replication within the Linux kernel, completely software-oriented. It's been merged with the mainline kernel since 2633. Many distributions already ship with it, but those that don't, you can add it real quickly with a kernel module. And here's what it looks like within Linux. As you can see, DRBD kind of sits between the file system and your block store. Any writes that are coming in to that device are then passed through DRBD, which pushes it down to your disk, as well as across the network, to your peer node, to the receiving DRBD, and down to its disk. This technology we're going to utilize in our demo to keep the data in sync between both geographically separated sites. And to allow DRBD to do that easily, we use DRBD proxy, which can be thought of as the WAN acceleration portion for DRBD. So previously, before Booth, we had 4-way redundancy with DRBD Stacking. With the newer DRBD 9, we should be able to achieve up to 32 replicas if needed, or you could still do a 4-way, as this example shows. For this, we have two 2-node Pacemaker clusters. These two clusters have no real knowledge of each other, and failover between the sites is done manually. And a quick graphic that kind of illustrates how that would work. The rectangles represent DRBD resources. The blue cylinders represent storage systems. In this case, it's a 4-node. We have Alice and Bob here locally. Bob is the active side, as shown in orange. The Charlie and Daisy is a passive site. And in order to fail over services from the one site to the remote site, it would have to be done. An admin would have to issue a few commands. Now, Booth allows us to automate that. And how Booth works is we utilize an additional arbitration node, or a ticket booth. This is housed in a separate location. And though the separate location is important, as we can't allow an outage in one location to dictate how Booth would behave. Only the cluster which holds the ticket may run the resources. This can kind of be thought of as the old token ring communications running the system, which had a token could transmit. And with these two new additional parts, we can now automate failover, as the ticket booth will revoke an old ticket, or the ticket will expire, and will then reissue a new ticket to the standby location. And a graphic which kind of shows that is here. As you can see, it essentially is the same cluster we had once before. We've just simply added a third arbitration node. It doesn't run any services. It just handles the quorum for the tickets. As we can see, the local site is currently active as it holds the ticket. Bob is still primary in this case, but the difference now is if this entire site was to go down or lose communication with the other two sites, this ticket would expire. We would make this the active ticket, and then Charlie here would go primary and start resuming services. So let me go ahead and demonstrate failover real quickly with some test systems of ours. Okay, so for our demonstration, we have two clusters One site is named Laboratory A and Laboratory B, while the peer site is named Sen7A Testing and Sen7B Testing. These are the two clusters. So we can see they're all connected via DRBD. The stacked resource is currently active on Laboratory B. It's currently in the primary state. And the peer site is going to look somewhat similar. Again, the stack site is active on Sen7B, but it is in the secondary state. And then the Laboratory A site is in a suburb here in Portland known as Beaverton, whereas the Sen7A testing site is located on the eastern side of Portland. So we're about 20 or so miles away from each other, nothing huge. And then we also have our arbitration node over here, which is located actually in the offices. So we have three distinct sites. As we can see, there is no cluster on the arbitration node. It is just simply running the booth service. And if we check, we can see that ticket A, the leader, is currently the 150.153. That is the virtual IP of this cluster over here. And if we check the status of the Pacemaker cluster, we can see that we still have two separate Pacemaker clusters, just the laboratory nodes on the side. Laboratory B is currently the primary, as shown here, master for the stack device, or for the stack device here. And for ours, we're simply running a DRBD-backed file system and a website hosted on this file system. That website is here at boothcluster.us.limbit. And it's a pretty simple website. We just have a graphic here kind of demonstrating how it works. Beaverton here is the laboratory cluster. Portland here is the Sen7 testing cluster. And then we have our arbitration on the side. The arrow here shows that the Beaverton site is currently primary. And over here we just have a simple log that updates every 30 seconds, letting us know which node's primary. For this demonstration, it's just this simple log that's replicated via DRBD. And this is replicated, as I said, via DRBD, utilizing proxy. And that's, let's see. And that I can demonstrate here. It's currently active over here. We're connecting Sen7A, this side to the laboratory side. It's up. We have some data that's been having compressions off in this case. And how proxy works is we buffer writes asynchronously to the local system memory. This helps us make sure that our WAN connectivity and our WAN latency between the sites doesn't become our disk throughput or our disk latency. So that's why you kind of need the proxy portion when you're doing geographically separated clusters. As I said, we're just simply replicating a log line, so there's very little memory usage in this demonstration. Now, for those of you not familiar with Pacemaker, let me go ahead and real quickly show a local failover. As we saw, as we saw, Lab B is the primary, and this site currently holds the ticket. So, just real quick for a demonstration, I'm going to hard power off our current primary, Laboratory B. And I do that by echoing B to proc sysrq trigger. For those who don't know, it's going to do a hard shutdown. It's not going to sync to disk. It's immediately going to reboot. And I'll do that now, and if we look up here, we'll see Pacemaker detect that and fail services over. detected the loss of B. It's now promoting to primary here. And very briefly, we'll have our site back up. And there it is. Our site and file system is now up on our web server. And if we go to our web page here, and I mean we can even hit refresh just to show everything failed over. And if we give it just a moment, there we go. Laboratory A is now the current primary. One other thing I want to demonstrate was the automatic recovery of DRBD. So everything has failed over, and because of the hard failure, we need to resync a little bit of data. As you can tell, not too much here. But everything automatically recovered and automatically connects, and in a few seconds here, everything's back to a nice healthy state, fully synced. B's rebooted, but it is now in the secondary role. As shown here, B is now the slave on the local site. And our web page is still chugging along, and everybody's happy. So now we'll move on to demonstrating Booth. As I said, it works on this notion of tickets. So for this demonstration, what I'm going to do is I'm going to set up some IP table rules that purely just block the Booth traffic. As I don't have local access machines, I don't want to block all traffic. But once we lose traffic to the rest of the cluster on the Booth, arbitration node and the peer site will pick up on that, let the ticket expire here, and then resume services elsewhere. The same thing would happen should a real disaster strike on both these systems get powered off, loss of power, or a network interruption. So I'm going to demonstrate that real quickly. Right now, A was the primary, so I'll block traffic there. And let me do that now. Just confirm. Yeah, our IP table rules are up. Okay, so the peer site does not have the ticket, and it's running some DRBD services and the Booth services, but as you can see, the website is not running there. It is running here. We have to wait for it to hit this expiration time, and then a few more seconds to allow stuff to stop before it starts here. As we can see, that was when it was granted. It'll expire here real quickly, in about a minute or so. Now, I mean, it's going to take a minute, but that's by design. With WAN connections, they can often be flaky, and we don't want the unnecessary failovers just because of minor network hiccups or anything of that sort. So it does take a second, but it is going to happen automatically. Very briefly here, in a few minutes. Right here is a nice live view of the cluster, as well as up here. And in a few more seconds here. Alright, here we go. The ticket has now been revoked. As it has expired, we see services stopping. And then if we come over here, as I said, it still takes another minute or two, as per design. Now, for this demo, I did stop the ports, but I mean, you could simply revoke the ticket manually and grant it elsewhere if you just want to move services, you know, as per an administrative task. So now we see the file systems up here, web servers up here, and that's all running on CentB. We go back to our website, refresh it. and we'll see that our log is now different, but the old logs are still there. Those were replicated. All the data is still there, and our graphic now shows that the Portland side is active. And it does take a few minutes, but the beautiful thing is it's now automatic. You could suffer an entire site failure or a power outage, and I mean, by the time the admins woken out of bed via the alerts, everything would already have recovered automatically. And at that point, the admin can now focus on what went wrong and why and what needs to be done, rather than things are out, we need to get them up quickly. So that's the newest little add-on to the Pacemaker HA stack, and we're very excited to now be supporting it and contributing to the project.